And the first speaker is Professor Murty. And about Professor Murty, he started his career just before 1980, though officially started on 1980, his PhD, and continuing research for 50 years on number theory, philosophy, and so many areas. He's basically an Indian mathematician working in Canada, and most of the number theories is influenced and by Professor Murty, including me. And he is a recipient of several awards, and mainly he published more than 300 research articles and produces more than 25 students for their PhD as a supervisor. And with this small remark, and he is also associated several chairs and other things in several places. And he is going to talk on Srinivasa Ramanujan, modular forms and beyond. I welcome Professor Ramanujan.
Okay, thanks. Thank you very much. Thank you to the organizers for setting up this wonderful conference where we can all learn about Mach modular forms, modular form, Mach modular forms, and beyond. So this lecture is by way of motivation, by way of introduction to perhaps the themes of the conference. So it's not going to go into gruesome detail, but it'll give you an overview of what you can expect. So let me begin with the elephant in the room. There's a fabled story in the Panchatantra of the blind men trying to figure out what an elephant is. It applies to many situations in human history, and particularly to the process of scientific discovery, especially as it pertains to our topic. So here you have the elephant, and each person is grabbing a part of it and tries to make a conclusion about the totality by only knowing a part. And so this is basically the problem of human knowledge, perhaps all of science itself, but certainly the topic of Mach modular forms and the discovery of Mach modular forms certainly has this element to it. So let me begin with the story of Ramanujan. Many of you know this, but doesn't hurt to repeat because it's absolutely extraordinary. The talk is literally about two letters, Tale of Two Letters, written by Ramanujan. First in 1913, where he introduces himself to G.H. Hardy and what he's been doing on. And the second letter was on his deathbed in 1920, outlining the theory of Mach modular forms. So we'll give an informal survey of these theories of modular forms, quasi-modular forms, and Mach modular forms. And I think they all owe their evolution to the personality and life of Ramanujan. Ramanujan had a mystic vision of mathematics in many ways and shaped the 20th century number theory, and now continues to shape the 21st century, going beyond number theory into combinatorics, into representation theory, and even mathematical physics. I have to say, on a personal note, I had John Carlo Rota as one of my mentors, and his mission in life had been to put combinatorics on the same foundational platform as algebraic geometry or number theory. And to this extent, I think he succeeded in many ways, and much of Ramanujan's work, especially with the partition function and quasi-modular forms and Mach modular forms, is very combinatorial in nature. So Ramanujan's a short life of 32 years did not give him enough time to develop many of these ideas, so he formulated them only in outline, but with profound intuition and insight. So it's become so popular that the story of Ramanujan has become a Hollywood movie, not a Bollywood movie, a Hollywood movie. And frankly, this movie is not too bad. It's very well done. So, the quotation attributed to Eichler is the following joke. There are only 5 operations in mathematics: addition, subtraction, multiplication, division, and modular forms. So you can see now how important the idea of modular forms has to be. If one had to point to a single mathematical idea that transformed 20th century mathematics, it would have to be the concept of a modular form. And this would be no exaggeration. I want to prove that to you. Ramanujan did not discover this idea because it already existed in the 19th century. However, he brought it to the foreground. He connected it to number theory and made it the centerpiece of his attention and the centerpiece of much of the attention of mathematics, especially number theory in the 20th century and now in the 21st century. So his 1916 paper, modestly titled On Certain Arithmetical Functions, had a tremendous impact on number theory of the 20th century. So if anyone, youngsters in particular, has not read this particular paper, I would invite them to do so because it's really full of inspiring ideas. It led to the development of the theory of modular forms and now emerging theory of mock modular forms, which was hastily described by Ramanujan at the end of his life. So the 1916 paper sowed the seeds of the theory of automorphic forms, which gave rise to what's popularly now known as the Langland's program. It led to an expansion of our idea of a zeta function and brought the marriage between number theory and algebraic geometry, which was not there in the 19th century. Although many attempts were made by Dedekind and others to kind of marry together these two topics, there was no foundations even for algebraic geometry. Now, Ramanujan's conjectures were solved using this connection. So it's always important to understand the role of a conjecture. A conjecture, a very good conjecture, can play the role of an inspiring muse that will activate, animate, and lead to a stupendous evolution of a subject. So in this context, Ramanujan's conjectures led to this speedy evolution of this particular two topics. The theory also led to the classification of finite simple groups using the monster group, as many of you know, monster group and the moonshine phenomenon constructed via modular forms and the theory of Botchard's products and so on and so forth. The theory of modular forms was central to the proof of Fermat's last theorem. You wouldn't have a proof of Fermat's last theorem without modularity of elliptic curves. Now, mock modular forms are emerging to describe the birth of the cosmos in theoretical physics, and from Professor Ashok Sen, we will probably learn a little bit more later in this conference. But let me begin with the story of G.H. Hardy and his discovery of Ramanujan. I have to say, discovery of Ramanujan is the appropriate word for what happened. In his 1936 lectures of Hardy, here he is. He had to give some lectures at Harvard University. So that was about, 16 years after Ramanujan's death. Also around the time that Hecke completed his theory, 1936. So here was G.H. Hardy, commissioned with the task of summarizing Ramanujan's life. And he was not only summarizing Ramanujan's life, but I have a feeling he was actually doing a retrospective on his own life. These lectures were later published as a book. And if you actually take these 12 lectures and read them very carefully, they're more stimulating than a novel because they actually bring tears, especially the introduction brings tears to the eyes, full of emotion there. They comprise a faithful snapshot of Ramanujan along with his main contributions of mathematics. Hardy confesses that Ramanujan was the most romantic figure in the recent history of mathematics and a very great mathematician. Now you have to understand this. Some of you have read Hardy's famous essay on mathematician's apology and his asinine idea that a mathematician is finished by the age of 40. He probably applied it to himself. And looking back, he sees that some of his best work had been done early with Ramanujan, and Littlewood. These are the two people he highlights that he collaborated with, and he was very grateful for that. So Ramanujan's story has all the fascination, the enchantment of a fairy tale, literally. That's why I'd say it's fascinating. It's far more captivating than even a novel. Truth is sometimes stranger than fiction. It was a real life story with enormous consequences for mathematics and more generally for science. So Ramanujan's letter to Hardy, the 1913 letter, Hardy knew full well that he was the first mathematician to take Ramanujan seriously. Earlier, Ramanujan had written to 3 other reputable mathematicians. I don't know if you know all this, but this is brought out in Bruce Barron's essays, which that's where I learned it. He'd written to 3 other reputable mathematicians in England. These were Baker, Hobson, and Hill. And I don't know which one, but one of them was extremely rude. Have to figure that out. But none of them, the 2 of them didn't bother replying. Hardy was the first to respond to his now famous letter on 16 January 1913. And the letter is very humble opening. Dear sir, I beg to introduce myself to you as a clerk. I have had no university education, but I'm striking out a new path for myself. I have made a special investigation of divergence series in general, and the results I get are termed by the local mathematicians as startling. Now, as I keep saying to my students, postdocs, colleagues, and so on and so forth, research is a form of unlearning, not learning. So you may know what has been done before, but you really have to do it with yourself, with bare hands. You have to recreate much of the mathematics. So here was Ramanujan, who had recreated all of 19th century number theory by himself with his bare hands. He didn't read many books. So what was in this letter? 2 entries of the first letter may be of interest to general audience. They're startling indeed. One is that the sum of the natural numbers is -1/12. The sum of the first cubes is 1/120. Of course, these are striking for the novice. Both of these have to do with summability of divergent series. One method, but not the only one, has to do with the method of analytic continuation, which is a topic in complex analysis. The 2 relations become evident if you consider the Riemann zeta function and the problem of analytic continuation and evaluate the zeta function at -1 and -3. So you end up getting these values. So this was known to Riemann, but Ramanujan never read Riemann. So he was redoing many of these things in his own way without complex analysis. And this is, I think, divergent series should be brought back into vogue. So actually, it's already there. It's in the theory of operator algebras. But anyway, it's worth looking into it in more detail from a classical perspective. So this means Ramanujan had other methods of summing divergences which were not based on complex analysis. Here are sample pages of the letter. First, I want to outline the beautiful handwriting. Can you write like that? You see, with the advent of computers, we're losing the ability to write. You know, there's a famous story of dialogues between Socrates and Plato. Plato was singing the praises of writing to Socrates, saying, now we can write things. And Socrates' response was, well, there goes the power of memory. And now, with computer technology, we're losing the ability to write. But anyway, that's beautiful handwriting. So this is the first page of Ramanujan's letter to Hardy. After a brief introduction, it goes on for 10 pages, giving theorem after theorem, formula after formula. So here it is. This is now the typeset from the book of Hardy's 12 lectures. One particular formula has to catch your eye. It's going to play a special attention role in our talk. It's this particular formula. It's trying to compute the coefficient of a certain power series, but this happens to be a theta function of weight minus a half. So that's really what he's doing there. Okay, there's more. Here's another interesting formula. This is actually a formula discovered by Riemann, but I told you Ramanujan never read Riemann. How did he find this? The number of primes in terms of the logarithmic integral. An explicit formula. This is an explicit formula with the Mobius function. So he found that. So there are many, many things. So here are the first couple of things that I talked about at the beginning. There. All right. More formulas. This is the letter. So essentially, the letter contained 120 theorems. And so when Hardy received this letter, he was confused as to what to make of it. Was Ramanujan a crank or a genius? And so he sat up all night, actually well into the morning, around 3 in the morning. So he invited his colleague Littlewood, and together they sat with the letter well past midnight. After 3 hours of careful study, they concluded a single look at them is enough to show that they could only be written down by a mathematician of the highest class. They must be true, because if they were not true, no one would have the imagination to write them down. Isn't that amazing? Can you imagine that night? So Hardy invited Ramanujan to come to England in 1914 against the backdrop of the First World War. Now, one formula in this first letter, as I said, is worth highlighting for this exposition. It is formula 7 of, in section 7, I talked about it in the previous slide. It was this coefficient of x to the n in this inverse power series is the nearest integer to this linear combination of the hyperbolic functions. And notice that these things grow like e to the pi root n. These terms grow like e to the pi root n over n. So this is the rate of growth of modular forms of negative weight. This is it's a precursor to that. Though this is not exactly correct, it's approximately true. The reciprocal of the power series appearing in the middle of the formula is a modular form of weight minus a half. And the last expression can be written as a derivative of this hyperbolic sine pi root n over pi root n. And this is important because this is the first term in what is called Rademacher's explicit formula for the partition function. These are the kind of terms that appear. This cannot be derived without the circle method and shows that Ramanujan had the idea before he got to England. Now, the Hardy-Ramanujan collaboration is an amazing collaboration. There are 2 big discoveries of this. First is the normal order method, which led to the development of probabilistic number theory. This says that the usual random number prime factors of a random number n is log n. And the second work is the asymptotic formula for the number of partitions of n, which led, of course, to the development of the circle method. I may have more things to say about the circle method and its applications in my other talk later in this week. But the thing that captured Ramanujan's attention and affection, perhaps, and seduction, is the tau function. It is a single-authored 1916 paper on the tau function that is the breakthrough paper of the 20th century. The function is defined by a very simple power series, and you take this product, infinite product, where is this thing? Infinite product, and you take this, raise it to the 24th power, and you expand, and these numbers to tau of n show up. Though Ramanujan did not invent the idea of a modular form, he can be credited with the discovery of mock modular forms. His last letter begins with these kind of functions and continues in this grandiose way about what is to appear in the future. He certainly saw a grand theory, which only now seems to be entering center stage, not only in number theory, but in other branches of mathematics as well. So what are these Ramanujan conjectures? So I mentioned already that the coefficients are given by this infinite product, y24, well, we'll see that in a second. And Ramanujan was not averse to computation. This is an interesting facet of great minds. I think they are not averse to doing menial calculation. Newton was like this too. He would calculate, thousands and thousands of decimal places of square root 2 for some reason. Ramanujan did the same with respect to the tau function. And you and I might just write a first 4 or 5 at best, but not perhaps beyond. But Ramanujan, being Ramanujan, he wrote this down, and he noticed that minus 24, the coefficient of q squared, times 252, which is the coefficient of q cubed, ends up being the coefficient here. So he started noticing patterns in these numbers. They'll get bigger and bigger very fast. But he started noticing patterns with these numbers, multiplicative properties. So he formulated some conjectures. First, that it seemed tau is a multiplicative function, tau satisfies a second order recurrence relation. I don't know how he found that. I guess if you start comparing the second coefficient, fourth coefficient, and the eighth coefficient, you start seeing some patterns. But it's not multiplicative relation, but it's a second order recurrence relation. So that also requires a little bit of, ingenuity and tenacity of purpose. So he certainly found that. And then finally, this remarkable conjecture that tau of p is always less than 2 times p to the 11 halves. So it gives you an idea of the growth of these coefficients. I was always trying to imagine how Ramanujan would have come up with this. And I have some theories as to how he would do this. But clearly, these are the conjectures that led to the development of the theory of modular forms. And certainly, Mordell proved the first two, but Hecke actually developed the theory, which Mordell could have done, but he did not do. So the precise form of these conjectures are, this is the precise recursion. And I suppose he found this multiplicative property and associated a Dirichlet series with the tau function, and noticed that the Euler product, unlike the zeta function, was not an Euler product of order 1, but it was a quadratic Euler product. And I assume to make that quadratic Euler product positive definite, I believe is the reason for putting this down. That would be my understanding of why he would do this. So the first two conjectures were proved by Mordell in 1917. They signal a general theory developed later by Hecke in 1935. So this is again a case in point. We can always learn from the mistakes of history. The mistake that Mordell made was not to recognize it was a bigger pattern. He could have done it. Actually, even if you check Hecke very carefully, all he really does is level 1. I mean, he starts the higher level, but he doesn't get it, right? I mean, it's all the Atkin-Lehner theory is what we need. That's the 1970s stuff. It was not there in the 1930s. So you see, Hecke did level 1. Level 1 could have been completed by Mordell. So the third conjecture is the deep one, was proved by Deligne in 1974 as a consequence of his solution to the Weil conjectures, and he was awarded the Fields Medal for this. So that's a big deal, because to connect these coefficients to geometry, counting points on varieties, was a big idea. That was an idea that he started slowly emerging with Sato, who developed the Sato variety, and said, maybe this has something to do with it. What you had to do is desingularize it and make it smooth. And that was done by Deligne. And once he did that, and Shimura, of course, also contributed to this process of desingularization and smoothening of that particular variety. But it was Deligne who finally showed it fits neatly into the Weil conjectures by that. The other thing, that's just the arithmetical or analytical side, the other thing that Ramanujan had noticed was that there are some special congruences that emerge for the tau function. Namely, tau n is always congruent to some of the 11th powers of the divisors of n, modulo 691. See, this is again an important part of being a scientist, mathematics. Do not ignore any property that you might think is irrelevant. It may be relevant, so put it down. So here, mod 691, to Hardy, it was a curiosity. And poor Hardy didn't actually ever appreciate the tau function. He says so in his things. And the reason is because he was coming from another angle. But there's something Galois theoretic, which is emerging, especially with the 691. It was only later in the 1970s, actually, the way Deligne had proved the Ramanujan conjecture, there's a Galois representation. That means Galois representation of the Galois group, Q bar over Q, into GL2 of the L-adic integers, such that the trace of the Frobenius automorphism, every prime has a certain decomposition group. There's a canonical generator called the Frobenius automorphism. You take the trace of that automorphism, it turns out to be tau of p. There's an interpretation, a Galois theoretic interpretation of tau, which we didn't have before. It's responsible for many things. So this is a big deal. It is this representation that explains the Ramanujan congruence, because that representation is ramified at 691. That's why you get these special congruences. So also all of a sudden, the ramification theory of the elliptic representation gives rise to an understanding, a theoretical understanding of these special congruences. It was Hecke who proved or developed the theory of modular forms of level 1, 1935. So it's a kind of a strange thing because this was happening early. Ramanujan died in 1920. He had made these conjectures in 1916. Mordell had proved in 1970. I find it rather puzzling that there's a 20-year gap, even though the theory is almost mutatis mutandis of Mordell's work. But not completely, of course, but you have to come up with these Hecke operators. The Hecke operators are actually there. If you read the Mordell paper, the Hecke operators are right there, staring at you. So Hecke just formalized that. All right, so this is what's called Hecke theory today. So what is a modular form? Mathematics can be said to be the study of symmetries of objects, and it is amazing that a set of such symmetries forms a group. When we look at the cosmos and see the symmetries and beauty, we literally see an all-pervading presence of mathematics. So you actually, when you say something is beautiful, you're actually saying something is mathematically symmetric, So there's a kind of the idea of beauty is inherent in the idea of mathematics, mathematical symmetries. So mathematics is omnipresent. It can be said to be omniscient too. The set of complex numbers with imaginary part, the upper half plane, seems to be the presiding deity of this holy grail of mathematical wisdom. The group of 2x2 matrices with integer entries, determinant 1, acts on the upper half plane by the usual fractional linear transformation. Z goes to AZ plus B over CZ plus D. And in other words, SL2Z is the group of symmetries of the upper half plane. This group action of the upper half plane seems to be at the heart of the cosmos. And this is what I was alluding to with the theory of Mach modular forms and black holes and whatnot. That's in string theory that we may hear more about from Professor Sen on Friday. Now, the space of modular forms of a fixed weight K is defined, is a collection of all these holomorphic functions on the upper half plane that satisfy this particular transformation law. And they have a Fourier expansion at infinity. They have actually a Fourier expansion at all the cusps. We'll not talk about that just yet. And these numbers, A sub f of n, are the numbers that are of significance. They end up having arithmetical, analytical significance. If we relax, if we say that the thing vanishes at infinity or at all the cusps, we call it a cusp form. If we relax the condition of holomorphy to be meromorphic at infinity, we end up getting the weakly holomorphic, like the J function, for example. Gentle introduction to modular forms for students who are new to this topic can be found in my book by Michael Dewar and Hester Graves, published by the Hindustan Book Agency in the IMSC lecture notes series. This cover, by the way, was suggested by me. I suggested a whole banana leaf with the water droplets, but the artist of the book publisher said that's a bit too gaudy, so we'll just put it in the corner. Too bad. All right. The vector space of modular forms. So you have these spaces. They're cusp forms, modular forms, weakly holomorphic forms. So you have a set inclusion. SK is the set of cusp forms. MK is modular forms. MK shriek is weakly holomorphic modular forms. So you have this set containment. Ramanujan observed that the growth rate of Fourier coefficients for each of these spaces is different. And now, if we put Q equals e to the 2 pi I z in the previous slide, you have a cusp form of weight 12, and that was the tau function. So the tau function was this typical, prototypical, I would say, prototypical element of SK. And the Eisenstein series are prototypical elements of these MK. So you kind of And the J function is the prototypical element of MK shriek. So you have these classical examples of this stuff. So you could construct modular forms with your bare hands. Here's a construction of what are called Eisenstein series. So simple exercise. You take this series, it converges for k bigger than or equal to 4, and it transforms according to the modular property that I defined in the previous slide. And so this is a construction of modular forms of weight k for k bigger than or equal to 4. And these are called Eisenstein series. You normalize them. You normalize them by dividing by 2 zeta k. And then you end up getting the Fourier expansion of these Eisenstein series as the classical divisor function. So the classical divisor functions of analytic number theory appear as Fourier coefficients of the Eisenstein series. This is a big idea of mathematics. So here, Bk is, of course, the kth Bernoulli number. The J function in the monster group, of course, if you take that E4 cubed and divide it by the Ramanujan cusp form, you end up getting the J function. So you can construct the J function also just from these objects. And these numbers have significance. They were noticed first by John Mackay, who observed that, hey, these numbers look like integer linear combinations of sums of degrees of irreducible representation of the monster group. And that was a passing observation, by the way. Passing, because I know John Mackay, he told me that it was a casual observation that he made, and it turned out to be a big deal. So don't ignore passing observations. It turned out to be a big deal. This is all the genesis of monstrous moonshine. So connecting group theory and modular forms. So you have now a big idea. This passing observation of John Mackay led to the classification of finite simple groups, a remarkable achievement of 20th century mathematics. Now, I told you that Ramanujan played with congruences. Well, the Eisenstein series he called P, Q, and R. So Q and R were already seen. Q was E4 and R was E6, but P is E2. Now, it turns out that E2 is not a modular form of E2. I'll talk about that in a second. So E4 and E6 were denoted Q and R respectively. Of special interest is E2, because when you put k equals 2 in that series I gave you for GK in the previous slide, it doesn't converge. Well, that was Hurwitz's PhD thesis, to make it converge. And so Hurwitz is the guy who discovered E2. Now, called P, and Ramanujan noticed but did not prove that all quasi-modular forms are generated by P, Q, and R. So we'll talk a little bit about this derivative operator. How is the space of modular forms affected by derivation or differentiation? Now, in the case of quasi-modular forms, this was proved that all quasi-modular forms, I'll talk a little bit about quasi-modular in a second, essentially is generated by P, Q, and R. You can think of a quasi-modular form as a modular form generated in the algebra of P, Q, and R. Good enough. So the interesting thing is, this was later proved by Kaneko and Zwegers, and again, we come back to the famous focus of attention. Ramanujan cusp form can be written in terms of E4 and E6, but you have to divide by 1728 to get the thing. Now that reader will observe the denominator is one less than the famous taxi cab number, and how could I not tell you this story? It's supposed to be a general audience talk. So interesting story about the number connected to Ramanujan's life when he was ill in a sanitarium. Hardy came to visit him in a taxi, and on entering Ramanujan's room, Hardy said, well, I just came in a taxi number 1729, which looks like a dull number. I hope it's not a bad omen. And Ramanujan says, well, on the contrary, it's very interesting. It's the smallest number that can be written as a sum of two cubes in two different ways. And Hardy then asked if he knew the answer for the corresponding problem for fourth powers. After a moment's thought, Ramanujan said he could see no obvious example, and then thought that if there is one, it must be very large. And indeed, the smallest number is 635,380,657. And here are the two representations as sum of force powers. Now, what this story tells is, as much as it's rather romantic and interesting that Ramanujan had this fascination for numbers, et cetera, sadly, it tells something about Hardy. That's what it tells. You know, the modular function is an important function, even in analysis, even in complex analysis. Okay, you can't miss the 1729. Now, differential equations for P, Q, and R. So I told you about this differential operator. And Ramanujan noticed there's a nice relationship between these differential equations. You have this matrix system of equations. And the significance of this is that it enables us to endow the set of all modular forms with an algebraic structure. This can be described as follows. It was already mentioned that E2 is not a modular form, but if you subtract this 3 over pi y, it becomes modular, but it's no longer holomorphic because you've put this, y is the imaginary part. It's not holomorphic, but it is modular now. So E2 star transforms like a modular form of E2. E2 of Z is holomorphic, but not modular, but E2 star is modular, but not holomorphic. A theme that repeats itself in the theory of modular form. The difference between the two is a real analytic function, and it is this sort of behavior that is characteristic of Mach modular forms, as we will see later. In fact, E2 is the simplest example of a Mach modular form. Actually, the first Mach modular form seems to have been discovered by Hurwitz in his thesis. So that's an interesting curiosity. Now, Ramanujan delta function is connected to the E2 in this fashion. And derivatives of modular forms are rarely modular forms. So Ramanujan's D operator allows us to define a differentiation, which is now called Ramanujan-Serre derivative, which maps the space of modular forms of weight k into space of modular forms of weight k plus 2. This differential operator has this nice functorial property. Another related application to the D operator is what's called the Rankine-Cohen bracket, which you can construct by taking successive Ds with this combinatorial thing. And it turns out this is a modular form of weight k plus L plus 2n. And this allows us to endow the space of modular forms with the Lie algebra structure. So there's all this connection to Lie algebras as well from the theory of modular forms. Now, so I already highlighted the fact that this differentiation operator is the natural curiosity. You know, you and I, a typical graduate student would just say, hey, what happens if you differentiate a modular form? Oh, drat, it is not a modular form, and then we stop. But no, you try to continue this thing. So the question of this differentiation, what is it? Holomorphy, as all of you know, is characterized by the Cauchy-Riemann equations. It can also be characterized by the fact that it satisfies the Laplace equation. Now, functions which satisfy Laplace equations are called harmonic functions. So instead of considering holomorphic functions, you may consider harmonic functions. It's a larger theory which will include the complex analysis case. So this is the idea of Maass. Maass was the first to study real analytic modular forms satisfying the above equation. In fact, he gave a course of lectures in the 1950s at the Tata Institute before it was formally built. He realized we need to define something more general than Laplacian. So we look at this generalized Laplace operator, delta K operator, which will of course appear in many of the tech lectures here, with a shift. And then that way he considered now functions on the upper half plane, which are real analytic. That means analytic in the two variables x and y. And then analytic, meaning infinitely differentiable, smooth. And then they have this transformation property, where is it? Here, for all the elements. Their solution to the generalized Laplace equation and meromorphic at infinity. So this gives rise to the space of Maass forms. And then we have now, obviously, you go back to Ramanujan's fundamental paper and ask, hey, is there something similar? Is there are there eigenfunctions of Hecke? What are Hecke operators here? And Hecke operators never had any holomorphy attached to them. It's just a linear operator. Hecke operators are nothing but linear transformations on vector spaces. So this is a vector space and it still works. So you have the theory of Hecke operators that you have to redo. And then the eigenvalues of the Hecke operators are the coefficients of these Maass forms. The question now arises, do they satisfy this this whole business of Ramanujan conjectures? And the answer is, we have the first and second analogs established, but the third Ramanujan conjecture about the coefficients satisfying a certain estimate is still an open problem, which fits neatly, by the way, in the theory of the Langlands program, because once you generalize the notion of a modular form to an automorphic form, it fits neatly that the Ramanujan conjecture generalizes not only for GL2, so this is all GL2, it will generalize to GLM. Another aspect that is new, I think, that's emerging from the theory of modular forms is some of the connections to transcendental number theory. The Fourier coefficients of Maass forms generically. Why I say generically is it's possible to create Maass forms corresponding to the eigenvalue of half or something where you get degenerate Maass forms where the Ramanujan conjecture can actually be proved in those cases. But apart from that, we expect that those Fourier coefficients are transcendental numbers, apart from those small set of counterexamples. Now we come to harmonic Maass forms of manageable growth. So these observations led to the discovery of new spaces of generalized real analytic forms. And they are, so instead of looking at the meromorphy at infinity, we'll now consider the growth rate in that. So it's allowed to grow maybe exponentially. And so we have this containment of these harmonic Maass forms. So elements of these Maass space are called harmonic Maass forms. And those which are of manageable growth, we will call them HK shriek. So MK shriek is then contained in HK shriek. So far, we've restricted our attention to the positive integral K, but as we'll see, half integral weight is important and even real numbers are important. Now, the partition function is also a topic that Ramanujan and Hardy had worked on, especially developing the circle method. And as I said, I'll talk more about this in my Thursday lecture, I think it is, Thursday or Wednesday lecture. Okay, so Wednesday lecture. And I'll say a few more words, but let me just say the definition of the partition function, I think most of you know, is the number of ways of writing any number n as a sum of parts, and we don't care about the order. So we don't count 3 plus 1 as different from 1 plus 3. We always write our partitions in decreasing order, and then that spells it out. So now the question is, how do you determine the size or the growth rate of P of n? Well, it grows very rapidly, and he noticed that this is the Fourier coefficient of modular form weight minus a half, which is the reciprocal of the eta function. By contrast, the tau function is the Fourier coefficient of modular form weight 12. So this weight business determines the growth rate, whether integral weight, positive weight, and so on and so forth, versus negative weight. So that's the first observation. One way to visualize partitions is what's called the theory of Young diagrams. So here you can see what's called a Young diagram. So corresponding to a partition lambda 1 to lambda k, you put lambda 1 nodes on the first row, lambda 2 nodes on the second row, and so on and so forth, and you get this kind of picture. And the Durfee square of such a diagram is the largest square of nodes in the upper left-hand corner. So this determines, so you take the largest square that you could form, that's called the Durfee square. And so that cuts the diagram into two pieces. One piece with smaller parts, both of them have smaller number of partitions, but they do not exceed the side length of the Durfee square. So if you ask yourself the question of how many ways can I write n as parts which do not exceed m, then you can see that this is the generating function for that function. And the study of these formal series puts naturally to a theory of modular forms, which you apparently saw at the end of his life. This has some connection to Mach modular forms as well. If you look at the B sub m of n is the number of partitions of n with Durfee square of size m, then you can see that the Durfee square of size m will correspond to q to the m squared. And then now I've got these two little pieces. And how many ways I can, well, I just take the square of that generating function. And so I can see immediately that this is the, so you see how important it is to understand visualization. Combinatorial thought is done more easily by visualization and by power series, by generating or Q series or whatever you want to call these things. By using these generating functions, it's easier to see these things. If you try to prove them with your bare hands, it's not so easy to see. So this is obvious now. I hope it's obvious to everybody. You take your Young diagram, just take the Durfee square, and you count how many ways can I complete that with that particular square, and that's the number of ways you get it. And so if you add that up, you get an identity. You get an identity of the generating function for the partition function on the one hand is in terms of another, these things are called Eulerian series. So these are the kind of series that appear in the Rogers-Ramanujan identities. These are the kind of theories that appear in the theory of modular forms and so on and so forth. So this is an important observation. Before his arrival in England, Ramanujan had discovered variations of these identities. So these are the couple of the other things that he discovered, that if you restrict yourself to progressions congruent to 1 and 4 on this left-hand side, you get this identity. 2 and 3, you get this identity. So you started noticing these nice, interesting combinatorial patterns. Now, Ramanujan had no proofs for either of these, but in 1917, while in England, and sitting in the library of Trinity College, he stumbled upon some old volumes of the Proceedings of the London Math Society, where he found an 1894 paper of Rogers in which these identities were proved. Hardy later recalled, I can remember very well his surprise and admiration which he expressed for Rogers' work. A correspondence between them followed, in the course of which Rogers was led to a considerable simplification of his original proof. These identities are now called Rogers-Ramanujan identities. So you see, this is, and again, what Professor Gopakumar was mentioning, the importance of browsing leisurely without any pressure of time in the library, handling good old-fashioned books and not PDF files. So in the 1918 paper, Hardy and Ramanujan derived this asymptotic formula, e to the pi root 2n over 3 over 4 n root 3. Remember I mentioned that this had similarity with the entry number 7 in Ramanujan's first letter. 20 years later, Rademacher discovered an explicit formula. Hey, this this looks awfully familiar. So this is an explicit formula where ak of n is given by these Dedekind sums, exponential sums of Dedekind sums. Now, Selberg writes that if Hardy had looked at Ramanujan's first letter, they could have derived Rademacher's formula. So this is not me making things up. It's, By the way, Selberg also made some contributions to the theory of modular forms. He has some papers on that. Before he got into, as an undergraduate, I think he was working on modular forms. So Ramanujan's last letter to Hardy, in his last letter, it's clear Ramanujan discovered an extension of the theory of modular form, was frantically trying to write down by giving examples what he called Mach theta functions. So for Ramanujan, theta function, modular form, more or less the same thing. So he writes these examples. So notice that they look very much similar to those right-hand side of the Rogers-Ramanujan identities, or that toy example I gave you with the Durfee square and all that, right? They look very close to that. So these have striking similarity with the series appearing in the Rogers-Ramanujan with some small sign changes. Now, when you talk about the analog of Fourier expansions of Mach modular forms, you need to bring in more notation. We are all familiar with the gamma function, and the incomplete gamma function is defined by this integral from u to infinity of that. So given a modular form of weight G, given a modular form G of weight 2 minus K with Fourier expansion, Bn to the n, we define G star using these Bn's in this formal sort of way. So Bn bar, gamma, this incomplete gamma function, and Q is either 2 pi I z. And this G star is called the shadow of G. Mach modular form H of weight K is a holomorphic function on H with at most exponential growth at infinity, which corresponds a shadow modular form G of weight 2 minus K, such that H of Z plus G star of Z now transforms like a modular form of weight K. So this, in the case of that toy example E2, H of Z would be E2 of Z, G of Z would be that 1 over pi y factor, and then this whole thing would be that E2 star that I had defined earlier in the thing. Coefficients of modular forms of Mach modular are still a mystery. Some have arithmetic meaning, others are expected to be transcendental numbers. So this is again something that is still in evolution. I have a theorem with Ekta Saha on some transcendental aspects of this incomplete gamma function. So if you take a complex number, x plus iy, such that pi y is rational, then gamma k minus 1 times comma 4 pi ny is always transcendental for any n. So this is a nice result that comes, we use non-trivial Siegel-Szydlowski theory in transcendental number theory. So it's an interesting application of that. All right, finally, I think my time is coming to an end. I just want to flash this particular slide. There's a nice connection between string theory and Mach modular forms. The theory of relativity and the discovery of quantum mechanics are the two pinnacles of 20th century physics. The former is the physics of the macrocosm, and the latter is the physics of the microcosm. Both theories work in the sense that they have been tested and observed phenomena are explained using that appropriate theory. However, the theories are incompatible. A good part of Einstein's later life was spent in search of a unified theory in which both quantum mechanics and relativity can be derived. And so such a theory has been proposed. It's called string theory. And it's essentially mathematically very elegant. Whether or not it works in real life, we don't know. Some say it does. But it proposes a unified theory which is mathematically elegant, and it may be the long sought after unified field theory. The traditional model holds that the fundamental particles resemble mathematical points like protons, electrons, and neutrons. But string theory says that these subatomic particles are vibratory phenomena, like a string. And each of these fundamental forces of nature, electricity, magnetism, and so on and so forth, these are all vibrational modes of strings. One of them is gravity, another is electromagnetic force, and so on and so forth. So the standard atomic theory is replaced by theory of vibrational modes. These strings are infinitesimally small. To get a sense of the microscopic size, the ratio of the size of a string to the size of a proton is about the size of a proton to the size of the entire solar system. That's a very, these can only be imagined mathematically, not visualized per se. So the mathematical theory of strings requires many dimensions. It has actually 10. These strings seem to vibrate in 10-dimensional space. I assume Professor Sen will talk more about this connection later. So Freeman Dyson, in one of his last lectures on Ramanujan, I was actually at the conference when Dyson was saying this thing. It was at, were you there in Urbana-Champaign, honoring, I think, Ramanujan? Yeah, well, no, yeah, it was at Urbana-Champaign conference. Ramanujan Revisited, I think there was a volume that was produced, right? Oh, you weren't there, okay. Yeah, I was there for that one. Dyson was there, and so was Subramanian Chandrasekhar. He was also there talking about Ramanujan and how Ramanujan influenced his life. Anyway, at that conference, Freeman Dyson was saying, the Mach theta functions give us a tantalizing hint that grand synthesis, still to be discovered, should be possible to build them into a coherent group theoretical structure. analogous to the structure of modular forms, which Hecke built around old data functions of Jacobi. This remains a challenge for the future. And I think we're now 20 years hence, we're getting there. And things are really developing very fast. That was the same conference, by the way, when Dean Hickerson had proved his crank conjecture. That's the time. So again, whimsical, flamboyant, cavalier observations that Dyson had made concerning ranks of partitions turn out to be connected to modular forms. Right? This is the way. So don't dismiss any of your brilliant observations as being irrelevant. So it seems we're on a cusp, no pun intended, of a new development, and the 21st century will see the emergence of a grand theory of modular forms, grander than the classical Hecke theory of the 20th century. Moreover, this theory may have a central role in unifying the diverse strands of fundamental particles, the holy grail of theoretical physics. So all the more reason for budding young scientists who are coming forward to learn and contribute to this new and exciting, and this conference is a great opportunity to learn these things. I'm hoping to learn many things myself. So the quantum theory of black holes is now a chapter in string theory, and a work by Murty and Zwegers. Certain generating functions that they produce that arise in this theory turn out to be modular forms. So that's an interesting phenomenon. So let me come back to the elephant that I started with, and quote this line from Aurobindo. On a height he stood that looked towards greater heights, our early approaches to the infinite, our sunrise splendors on a marvelous verge, while lingers yet unseen the glorious sun. What now we see is a shadow of what must come. So thank you for your attention.
Thank you, Professor Ramurthy, for his inspiring and wonderful introductory talk on these headings. And now I will leave the audience to ask a few more remarks or questions.
Yes.
For Maass form.
Yep.
The first two have been proved. Like who proved them?
Oh, it's Maass. Maass.
Oh, Maass.
So yeah, when he was developing, he developed that theory of operators for Maass forms. Yeah, no. And he developed the theory of Dirichlet series attached to eigenfunctions of Maass forms. Yeah, it's all there. Yeah, and he gave some examples for number fields using fundamental units of quadratic fields. All those examples exist there, for which he showed that Ramanujan conjecture is kind of, yeah.
And the third one is.
The third one is still open. The third one, that's an interesting thing. See, the third one is now set in context. This is the point. The point is, mathematics is not about proving theorems. It's making the right conjectures. Right conjectures, not only any old conjectures, right conjectures. So if you make a good conjecture, it can animate a lot of activity and set, so that observations, the power of observation, right? So yes, that thing is still open. The Ramanujan conjecture for Maass forms is still open. It has been, progress has been made from the automorphic side, by knowing higher power symmetric power L functions, you can, and using classical analytic number theory, you can get estimates for these coefficients. And the other thing that is interesting is that if you think about the Lindelof hypothesis in the level aspect, that has an interpretation as the Ramanujan conjecture for half-integral weight modular. That's one thing. And I would not be surprised if using Mach modular forms and moving to the harmonic Maass forms of weight 1/2, one may have a connection to ABC as well. I would not be surprised. Yeah. So there's a lot of that. This interpretation of the Ramanujan conjecture in this fashion leads you to understanding why can't you prove a theorem? Because we don't understand it. So if you have the right language, right formalism, you end up solving these things. The Grothendieck philosophy, of right language and right formalism.
I
Yes.
mentioned that the ring of quasi-modular forms of Whitney and level 1 is generated by P2 with the generators of some modular. Right?
Yeah,
So, do we know anything about the higher level man?
experts are here. Do we? Do we know anything about higher level? I would think so, but I would think so.
Possible to do a similar thing. Higher level means for congruence subgroups.
Yes.
Yes.
I think so. I think it's.
I want to know that is it? I mean, are you expecting that the generators of weight K level and quasi-modular forms are basically some generators of modular forms plus the duplications of E2 are
Something like that. I think that's that has been written down. I think somewhere. I have to check. Is it? Is it true? Okay, yeah, that's what I think so. I have to check. I'm not the expert, but thanks for asking the question. Yeah. Somebody had a question here. Oh, yes.
Paper of Selberg as an undergraduate student that you contribute to this area.
Yeah. I think he was messing around with some mock modular forms, actually. He has some papers on power series. You know this more about this?
Seventh order.
Yeah, seventh order mock theta function is a paper that Selberg wrote. Well, I think when he was an undergraduate or something, in Norwegian. In Norwegian. That's why maybe you may not have read it because it's in Norwegian. It's in his collected papers. Yeah.
Any other questions, remarks? Okay, let me thank the speaker again.